Hello everybody. Now we start the students' independent work with the teacher. Subject is data storage and manipulation. The discipline is information and communication technologies.
Databases and database technology are having a major impact on the growing use of computers. It's fair to say that databases play a critical role in almost all areas where computers are used, including business, electronic commerce, engineering, medicine, law, education, and library science, to name a few. A database is a collection of related data. By data, we mean known facts that can be recorded and that have implicit meaning. For example, consider the names, telephone numbers, and addresses of the people you know. This is a collection of related data with an implicit meaning and hence is a database. A database has the following implicit properties. A database represents some aspect of the real world, sometimes called the mini-world or the universe of discourses, DOD. Changes to the mini-world are reflected in the database. A database is a logically coherent collection of data with some inherent meaning. A random assortment of data cannot correctly be referred to as a database. A database is designed, built, and populated with data for a specific purpose. A database can be of any size and of varying complexity. A database may be generated and maintained manually, or it may be computerized. A computerized database may be created and maintained either by a group of application programs written specifically for that task or by a database management system. A database management system, DBMS, is a collection of programs that enables users to create and maintain a database. The DBMS is hence a general-purpose software system that facilitates the process of defining, constructing, manipulating, and sharing databases among various users and applications. The database system contains not only the database itself, but also a complete definition or description of the DB structure and constraints. This definition is stored in the DBMS catalog, which contains information such as structure of each file, the type and storage format of each data item, and various constraints on the data. The information stored in the catalog is called metadata, and it describes the structure of the primary database. The architecture of DBMS packages has evolved from the early monolithic systems, where the whole DBMS software package was only tightly integrated system, to the modern DBMS packages that are modular in design with a client-server system architecture. In a basic client-server DBMS architecture, the system functionality is distributed between two types of models. Now we specify an architecture for database systems called the three-schema architecture that was proposed to help archive and visualize these characteristics. The three-schema architecture is also called ANSI Spark architecture or three-level architecture. This framework is used to describe the structure of a specific database system. The three-schema architecture is also used to separate the user application and physical database. It contains three levels that are presented in this diagram. The internal level has an internal schema which describes the physical storage structure of the database. The internal schema is also known as physical schema. It uses the physical data model. It used to define that how the data will be stored in a block. The physical level is used to describe complex low-level data structures in detail. The conceptual schema describes the design of a database at the conceptual level. Conceptual level is also known as logical level. The conceptual schema describes the structure of the whole database. The conceptual level describes what data are to be stored in the database and also describes what relationship exists among those data. In the conceptual level, internal details such as an implementation of the data structure are hidden. Programmers and database administrators work at this level. At the external level, a database contains several schemas that are sometimes called as sub-schema. The sub-schema is used to describe the different view of the database. An external schema is also known as view schema. Each view schema describes the database part that a particular user group is interested and hides the remaining database from that user group. The view schema describes the end-user interaction with database system. By structure of a database, we mean the data types, relationships, and constraints that should hold for the data. Most data models also include a set of basic operations for specifying retrievals and updates on the database. In addition to the basic operations provided by the data model, it's becoming more common to include concepts in the data model to specify the dynamic aspect or behavior of a database application. This allows the database designer to specify a set of valid, user-defined operations that allowed on the database objects. Common logical data models for databases include hierarchical database model, network model, relational model, post-relational database model, object model, and multidimensional model. The hierarchical model organizes data into a tree-like structure, where each record has a single parent or root. Sublink records are sorted in a particular order. That order is used as a physical order for storing the database. This model is good for describing many real-world relationships. This model was primarily used by IBM's information management system in the 60s and 70s, but they are rarely seen today due to certain operational influences. The hierarchical model is presented on this slide. The next model is the network model. The network model builds on the hierarchical model by allowing many-to-many relationships between linked records, implying multiple parent records. Based on the mathematical set theory, the model is constructed with sets of related records. Each set consists of one owner or parent record and one or more member or child records. A record can be a member or child in a multiply sets, allowing this model to convey complex relationships. It was most popular in the 70s after it was formally defined by the Coherence on Data Systems Languages, CODASYL. On this slide, you can see the example of the network model. The most common model, the relational model, sorts data into tables, also known as relations, each of which consists of columns and rows. Each column lists an attribute of the entire in question, such as price, zip code, or birth date. Together, the attributes in a relation are called a domain. A particular attribute or combination of attributes is chosen as primary key. That can be referred to in other tables when it's called a foreign key. Each row, also called a tuple, includes data about the specific instance of the entity in question, such as particular employer. The relational model is presented on this slide. So you can see a table which consists from attributes, rows, number of rows, and number of attributes. The model also accounts for the types of relationships between those tables, including one-to-one, one-to-many, and many-to-many relationships. Within the database, tables can be normalized or brought to comply with normalization rules that make the database flexible, adaptable, and scalable. When normalized, each piece of data is atomic or broken into the smallest useful pieces. Relational databases are typically written in structured query language, SQL. The model was introduced by Code in 1970. On this slide, you can see the example of the relational model. There are three tables that have relation with each other using primary and foreign keys. Object-oriented database model defines a database as a collection of objects or reusable software elements with accountable features and methods. The object-oriented database model is the best-known post-relational database model since it incorporated tables but isn't limited to tables. Such models are also known as hybrid database models. These models combine the simplicity of the relational model with some of the advanced functionality of the object-oriented database model. In essence, it allows designers to incorporate objects into a familiar table structure. The object-oriented model is presented on this slide. Multidimensional model is a variation of the relational model designed to facilitate improved analytical processing. While the relational model is optimized for online transaction processing, or LTP, this model is designed for online analytical processing, or LAP. Each cell in a dimensional database contains data about the dimensional tracked by the database. Visually, it's like a collection of cubes rather than two-dimensional tables. This is an example of multidimensional model. And now let's watch a small video about history of databases.
Our lives are flooded with all kinds of information. Thanks to computer databases, we interact with information easily and seamlessly on a daily basis. Databases were used to organize information long before the computer age. This Sumerian tablet is an index of medical prescriptions. Ship manifests, card catalogs, and product inventories are also databases. The computer allowed databases to be automated. Early computer databases followed a flat file model, a simple, consecutive list of records. But this format required that computers begin every search at the start of the list and search sequentially. This was a slow way to search and maintain large volumes of records. New, faster databases were needed that were expandable, reliable, and efficient. In the mid-1960s, IBM used a hierarchical model for their information management system, IMS. This tree-like structure, with parent nodes pointing to child nodes, was successfully used by NASA to manage drawings for the lunar lander. A more flexible network model was developed by GE's Charles Bachman. Now, child nodes could have multiple parents, but as the database got complicated, it was too hard to manage all those pointers. Ted Codd, a computer scientist at IBM, had a better idea. His relational database model, which he first proposed in 1970, organized a body of data into simple tables of related information. There were no pointers to maintain because tables are connected only by having matching data fields. This made it easier to access, merge, and change data. C.J. Date, an IBM instructor and author, was convinced that the relational database was a better model. Codd and Date wrote papers, lectured, and debated its merits. But Codd's relational database competed with another IBM product, the profitable IMS. So IBM was slow to support the new idea. In 1973, Michael Stonebreaker's team at UC Berkeley used Codd's idea to create the Ingress Relational Database, making it freely available for a modest fee. Several companies used it as the basis for successful commercial products. It took until 1975 for IBM to produce an experimental relational database named System R. It used a structured query language developed by IBM's Don Chamberlain and Raymond Boyce to search and modify data. A young entrepreneur named Larry Ellison was also intrigued with Codd's ideas. In 1977, he put up $2,000 of his own money to start a software company with Bob Miner and Ed Oates. Their mission? Develop and sell the first commercially available relational database compatible with IBM System R. Their flagship product was Oracle, which shipped in 1979. The first version ran on mini-computers, but by 1983, the company had rewritten it to run on many more computer systems, including IBM PCs and mainframes. Oracle quickly became profitable. In 1983, IBM finally released a full-fledged commercial relational database, DB2, for mainframes. But it was too late for IBM to dominate the mini-computer market, and Oracle was already selling to IBM's customers. Oracle had adopted Ted Codd's relational database concept early, when his own employer, IBM, wouldn't, and Oracle became one of the largest software companies in the world. Its success helped relational databases become the way much of our computer data is organized. Working, communicating, shopping, relaxing. Nearly everywhere we go, data is gathered, organized, and made accessible. In this age of information, a database is never far away.
Normalization is the process of efficiently organizing data in database. There are two goals of the normalization process: eliminating redundant data. For example, storing the same data in more than one table, and ensuring data dependencies make sense, only storing related data in a table. Both of these are worthy goals as they reduce the amount of space a database consumes and ensure that data is logically stored. The normalization process, as first proposed by Codd in 1972, takes a relation schema through a series of tests to certify whether it satisfies a certain normal form. The database community has developed a series of guidelines for ensuring that databases are normalized. They are referred to as normal forms and are numbered from 1, the lowest form of normalization, referred to as first normal form, or 1NF, through 5, fifth normal form, or 5NF. In practical applications, you'll often see 1NF, 2ndNF, and 3rd-NF, among with the occasional 4th-NF. Fifth normal form is very rarely to see.
So the work is over. Thank you for your attention. Goodbye.